Hey everybody, and welcome! Today, we're going to crack open one of the most essential electrical devices on the entire planet, the transformer. We're going to peel back the layers of perfect theory to get to the messy, fascinating, and practical reality that literally powers our world.
But let's start with something I know you've experienced. You unplug your phone, but you leave the charger plugged into the wall. You come back a few hours later, you touch it, and it's kind of warm, right? Why is it using energy when it's not even doing anything?
And that warmth, that's the key to our entire story today. It's the signature of an imperfect real-world device. So we're going to go on a little journey, from the perfect transformer you see in textbooks to the practical one in your wall, and uncover the 4 hidden flaws that explain that mysterious heat.
To really understand the real deal, we have to start with its perfect, theoretical cousin, the ideal transformer. Now this is the flawless, 100% efficient device you learn about in school, and it basically has 2 magical abilities. Okay, so its first magic trick? It all comes down to the super simple rule, EMF, or voltage, per turn. As long as you have different coils of wire wrapped around the same magnetic core, the voltage you get in any single loop of that wire is going to be exactly the same for all the coils. So if you get 1 volt per turn, a coil with 10 turns gives you 10 volts. A coil with 20 turns gets you 20 volts. It's that clean, elegant relationship that lets a transformer step voltage up or down so easily.
And this is where you see just how much the little physical details really matter. Let's say you have 2 coils on the output side, one giving you 50 volts, the other 30. Naturally, you want to combine them to get 80 volts total. But if you hook them up backwards, wrong polarity, their voltages actually fight each other. They subtract. So instead of 80 volts, you get 50 minus 30, just 20 volts. A tiny wiring mistake completely tanks your output.
Now for its other superpower, Impedance Transformation. This is its ability to change how the power source sees the thing it's connected to. A transformer can make a load look bigger or smaller, electrically speaking. It's like a pair of impedance binoculars, letting an engineer perfectly match a source to a load to get the most power out of it. It's pretty amazing.
Okay, so that ideal transformer? It's a beautiful idea in a textbook. But now it's time for a reality check. The device that's actually plugged into your wall is a true marvel of engineering for sure, but it has these unavoidable physical flaws that make it different from that perfect model.
All right, flaw number 1. This one's the most straightforward. The wires themselves. They're made of real copper, which has resistance. And we all know, anytime you push current through a resistance, you generate heat. This is just a basic power loss, plain and simple.
Next up, flaw number 2, leakage flux. See, in that perfect world, every single bit of the magnetic field from the first coil would zip right through the iron core and link up with the second coil. But in reality, some of that magnetic field just leaks out. It escapes into the air, completely missing the second coil. It's just wasted magnetic energy that doesn't do any work.
Third, the core itself isn't perfect. An ideal core, you can magnetize it with 0 effort. But a real iron core, it's a little stubborn. It needs some convincing. You have to feed it a little bit of what's called magnetizing current, just to get that magnetic field going in the first place. It's an energy cost the transformer has to pay just to be ready to go.
And this last flaw, this is the big one. This is core loss, specifically something called hysteresis. Remember, with AC power, the magnetic field in that core is flipping back and forth, 60 times a second. Imagine all the tiny little magnetic particles inside that iron being forced to snap around constantly. It creates a kind of internal magnetic friction, and that friction generates a lot of heat. And this is the main reason your idle charger feels warm.
So when you add all these flaws up, you get this really weird side effect. It creates this kind of ghost current that's always flowing, even when the transformer isn't doing any real work.
And that brings us right back to the big question we started with. Why is that charger sucking down power from the wall when your phone isn't even plugged in? Well, the answer is this ghost current.
Now, this thing has an official name, no-load current, and it's actually pretty small. Usually only about 2 to 5% of the current the transformer draws when it's working at full blast. But here's the thing. Even though it's tiny, it is always there, 24/7, as long as that charger is plugged in.
So what's this little current actually doing? Well, it's multitasking. It has 2 main jobs. A small part of it, the core loss component, is constantly supplying the energy that gets turned into heat from that magnetic friction we talked about. The other, bigger part, the magnetizing component, has the job of just keeping that magnetic field in the core up and running.
It's the price of admission for being on.
Okay, so you've got all these messy, real-world flaws and ghost currents. How on earth does an engineer work with that? Well, they do something brilliant. They translate all this messy physics into an elegant electrical blueprint. It's called an equivalent circuit, and here's how they piece it together. You start with the perfect, ideal transformer, right in the middle. Then, to represent the heat loss in the real copper wires, you add resistors. For that wasted magnetic energy, the leakage flux, you add some inductors. And finally, to account for that ghost current, you add a whole new side branch of components, one part for magnetizing the core and one part for its heat loss.
And what you get at the end is this, the exact equivalent circuit. I know, it looks a little intimidating, but it's an incredibly powerful tool. It's like a perfect electrical manual for a real transformer, flaws and all. With this diagram, an engineer can calculate exactly how it's going to perform in any situation.
Now that exact model, it's perfect, but solving the math for it can be a real pain. So for most everyday engineering, there's a fantastic shortcut they use.
And the whole reason this trick works, the real genius behind it, is remembering just how tiny that no-load current is. I mean, it's so small that its effect on the first few components in the circuit is practically zero. So engineers just take that whole branch for the core's energy needs and slide it from the middle right over to the very front. This one little move makes the math so much easier.
And this approximate model, it's an absolute game changer for engineers. It lets them just add up all the resistances into one number, do the same for all the leakage stuff, and it turns a really complex calculation into something much more manageable. It might not be 100% perfect, like the exact one, but it's more than accurate enough for pretty much any real-world job.
And that brings us full circle, right back to where we started. That warmth you feel coming off your charger isn't a defect. It's not broken. It's the physical evidence of all these real-world imperfections hard at work. The resistance in the wires, and especially those core losses, all being paid for by that tiny, constant no-load current. It's the signature of reality.
You know, this whole journey from a perfect idea in a textbook to a practical device in your hand is always a story of compromise and clever tricks to get around these built-in flaws. It kind of makes you wonder, doesn't it? What other perfect devices that you use every day are hiding the